Start, sir.
Welcome to Lab Session 2 of Plant Design and Economics. A very good afternoon. Today, we'll first talk about, we have already talked about before, but again, we'll just go through it, assignment policy and exam policy, because you are about to write your exam now. And then we'll briefly discuss an important effect about recycle streams. We call that as snowball effect. This presence of recycle stream in a process poses an important problems or issues during control of the process, particularly plant-wide control. So we'll briefly touch upon that, and then we'll look at some of the questions that that may be there on the portal. So first, about your examination date and time. Exam is scheduled on December 20, 2020. So it will be an online exam. The exam will be scheduled in 2 sessions. Morning session will run between 9 a.m. to 12 noon. And the afternoon session will be between 2 p.m. to 5 p.m. Then the evaluation policy is as follows. Your final score will have 2 components. One component will come from average assignment score. Another component will come from your exam score that you write on December 20. You have been given 12 assignments. So all 12 assignments will not be considered. Your best 8 assignments will be considered. So 25% of average of best 8 assignments out of the total 12 assignments given in the course will be considered for average assignment score. And 75% of the proctored certification exam score out of 100 will be considered as exam score. And final score then will be sum of average assignment score and exam score. Now there is eligibility criteria for obtaining a certificate for this course. You have to get at least 10 points out of 25 in average assignment score and 30 points out of 75 as exam score. Please note that both must be satisfied. Exam score 10 out of 25, assignment score 10 out of 25 and exam score 30 out of 75. Both must be met. Now, let's briefly talk about effect of recycle. We have discussed about recycle when we talked about first time we have talked about recycle when we talked about conceptual process synthesis in the context of design of reactor and its recycle stream. Then we discussed about separation systems. We discussed how reactor and recycle stream will influence the design of separation process, etc. We have seen that one of the most important uses of recycle stream is to suppress the production of undesirable byproducts. Minimizing the amount of toxic and dangerous undesirable components has become increasingly important with tighter pollution and safety standards. So recycle stream is very important. All unreacted reactants will be recycled back to the reactor. This will add to your process economics. Now, one of the basic issues with the recycle stream is that they can produce a drastic slowdown in the dynamic response of the entire integrated plant. What it means is that a process without a recycle stream and a process with a recycle stream will show completely different dynamic response. A process with a recycle stream will be much slower in dynamic response. For example, so distillation columns and reactors normally have a transient response, so that may be of the order of tens of minutes to few hours. But when you insert a recycle stream, the transient response of the coupled process may be in terms of days. So this is how it slows down the process dynamics. So response becomes very, very sluggish. Now, let us see why this happens. Let's consider a very general process block diagram. You are familiar with this block diagram. You have learned it in your process control class. So we have a forward process, and then there is a recycle stream. So input to the forward process is basically sum of the input that goes here as U and also the input that comes from the recycle process. That's basically output of the recycle process. Now, what we can do is, see, we can consider the dynamics of this forward process. We can also consider the dynamics of the recycle process, and then can find out the dynamics of this integrated process. So this is the simplest possible case. And to make the things very simple and the calculations easy, what we'll consider that both the forward process and the recycle process are characterized by first order dynamics. That means the forward process can be represented by first order transfer function, you know, Kp by tau s plus 1 kind of transfer function, and recycle process can also be expressed by a first order transfer function. So both represents first order process. So as we discussed that in the absence of recycle, the forward process receives Y as input. But when recycle is on, the input to the forward process Z is sum of U and X, where X is the output of the recycle process. Look, the input to the recycle process is Y, and output from the recycle process is X, which is added with U, and then X plus U, which is Z, becomes the input to the forward process. We consider that both the processes are first order process. Now let's recall your process control class. What do you mean by a first order process? A first order process can be characterized or represented or mathematically expressed by a first order differential equation. So let's consider this first order ordinary differential equation. Here, y is the output or response of the process, and f of t is input. Note that both y and f are functions of time. So y is the response or output, and f is the input. F input cell may be step input, it may be ramp input, it may be sinusoidal input, so on and so forth. Now what I have written, a1 dy dt plus a0y equal to b into f of t is a very general representation of a first order ordinary differential equation. Now let's divide this equation throughout by the coefficient of y, which is a0. Please note that a1, a0, b are the system parameters. Like when you analyze a process, for example, let us say we are talking about a process where only mass flow is involved. So you write a mass balance equation only. Let's say over a tank. You want to study how the level of the water in the tank changes with change in the input flow rate to the tank or output flow rate from the tank. So what is the physical phenomenon that is happening is changes in the mass of water in the tank. So you write down only mass balance equations. Similarly, in a heating reactor, suppose in a water heater, you'll be writing energy balance equations. Now, when you write this mass balance equation or energy balance equation for a process, to obtain an equation of like this, say first order differential equation for a first order process, this A1, A0, B will be the parameters of the physical process that you are considering. For example, let us say I'm writing down a mass balance equation for over a tank, water tank. So the parameters like say tank volume, which is say cross-sectional area into H. So A is the cross-sectional area of the tank will come into the equation. Similarly, this A1, A0, B all represent system related parameters. So divide this equation throughout by A0, there is the coefficient of the Y. Then in this form, this A1 by A0 always represents time constant of the process. And B by A0, this has to be 0. This represents the gain of the process. And this, if you take Laplace transforms, you get transfer function as k by tau s plus 1. This k is b by a0 and tau is a1 by a0. So tau into dy dt plus y equal to k into ft or any function as input represents a first order process. So I have two processes here. One is the forward process, another is the recycle process. So both are being considered as first order process. So I can write two first order differential equations for individual process. So let me first write down the first order differential equation for the forward process. Note that what we wrote in the previous slide was tau dy dt plus y equal to k, that gain, into input function. Note that input function is z is equal to x plus y. Sorry, u plus x. So this represents the forward process. First order differential equation representing forward process. Similarly, write the first order differential equation representing recycle process. What is the input to the recycle process? Y. And output is x. So this equation will be tau into dx dt, because x is now output, plus x equal to gain k into input y. So basically, both equation you can write by considering the general equation tau dy dt plus y equal to gain into input f of t. Note that tau f is the time constant for the forward process and kf is the gain for the forward process. Tau r is the time constant for the recycle process or recycle component, and kr is the process gain for the recycle process. Now these two first order processes together will represent the integrated process. Integrated process means the single process considering both forward process and recycle process. Because you have to finally you have to find out what is the response of this integrated process. So these two equations can be combined together to obtain the overall transfer function of the integrated process or overall behavior of the first order process. This basically can be represented like this. So forward transfer function and the recycle transfer function. So what you can also do is you can take ddt of this equation. So differentiate this equation, then you will have a dx dt term. So that dx dt term you replace using this equation. If you do that, you'll get a second order differential equation because you're taking derivative time ddt of this. So d square y dt square you'll get. So you'll get a second order differential equation. And you also can imagine that in that system there are two first order systems integrated. So the overall process response is going to be second order. So you'll obtain a second order differential equation which will represent a second order process, and the characteristic equation of that will be this. You just do this algebra, you'll obtain this. So now compare this equation with the well-known tau square s square plus 2 zeta tau s plus 1. And then you see that this term represents tau square. This term represents tau square. So tau or the time constant will be square root of this term. So the time constant of the overall process is the product of the individual processes time constant divided by 1 minus product of the individual process gains. So the overall second order system has time constant that depends on the time constant of the individual components, tau f, forward process time constant, tau r, recycle process time constant, and the product of the two process gains, kf and kr. So now if you look at this equation, overall time constant of the process, that means the time constant of the integrated process, will become large when the KR values becomes closer and closer to 1. So when KF and KR value becomes close to 1, then the value of the overall value of the time constant of the overall process increases. So here we plot several such situations. That means different values of KF into KR. For that we set KF, we set the time constant of the individual process at 1. That means tau F equal to 1, tau R equal to 1. So individual time constant have the values of 1 unit of time. And then for various cases of KF into KR, we plot response versus time. So this we are setting this value to different values by considering tau F, tau R equal to 1, and then finding out the response for a given, say, step input. So you have the transfer function. If we give step input for such situations, I can obtain the response. So these responses plotted as Y versus T. Now you note the behavior of the response. We know that the time constant for a first order process is the time that it takes the output to get to 63.2% of the final steady state value. That means, say, consider 6.32 here. So if we consider this case, KF into KR equal to 0.9, which is close to 1, note that the time constant becomes 20 units of time. Remember, the time constant is that value of the time which corresponds to the 63.2% of the final steady state value. So consider this case where KF into KR equal to 0.9. So this value is 63.2%. So the corresponding time is 20 units. So individual time constants are 1, but the integrated process time constant becomes 20 times. So this much the process is slowed down. So this is why presence of a recycle stream will drastically slow down the response of the overall process. Now let's come to the snowball effect. See, the snowball effect, you just consider a snowball that is falling down the hill. So as it rolls down, its effect becomes more stronger, more violent. So the snowball effects starts with a very small effect, but then goes on its magnitude with time. The recycle has similar effect. The flow rates of a recycle streams are often very sensitive to small disturbances. So a very small disturbance to a recycle stream can cause a very large change in the process. This is known as snowball effect. A small change in some variable, for example, fresh feed flow rate, can produce a very large change in the resulting flow rate of the recycle stream. So consider a reactor. Consider a reactor where you have a phase feed stream going in, and there's a recycle stream. Now, a small change in this phase feed flow rate can cause a large change in the flow rate of the recycle stream. We'll briefly take an example and see. Amplification factors of 3 are quite common. What do we mean here by amplification factor of 3? We mean that a 10% change in the feed flow rate can cause 30% change in the recycle flow rate. So a 10% change in the fresh feed flow rate to the reactor can cause a 30% change in the recycle stream flow rate. What is its implications? Let's consider the recycle stream from a distillation column. So if there is such 30% change in the recycle flow rate, so the loading in the column will change drastically. Vapor rates may get so high that the column floods or we run out of reboiler or condenser capacity. I saw one, okay, maybe I'll come to that one question that came on the forum. I'll come to that later. Let's consider this. Let me stress upon this point one more time. So if you consider a recycle stream from a distillation column, and there is such a huge change in the recycle flow rate, the loading in the column can change drastically. So the vapor rates may get so high that the column floods or we run out of reboiler or condenser capacity. Snowballing occurs because the conditions in the reactor have to change to accommodate the disturbance. Second, I increase the fresh feed rate by 10%. So what does it mean? It means that the reaction rates in the reactor must increase by 10%. If the volume and the temperature in the reactor are fixed, the only way a 10% increase in the reaction rate can be attained is by significant changes in the compositions of the reactants in the reactor. So how higher reactant concentrations are needed? Because there has to be 10% increase in the reaction rates. So higher reactant concentrations are required. And how do I get higher reactant concentrations? By increasing the recycle of reactant. So that's how the recycle rate will increase. So let's consider this example. This is an example of a reactor, let's say CSTR, where a reaction A to B takes place, which is a first order reaction. And if B is much more volatile than A, then the product stream, which will also contain unreactant A, can be separated by flash. So that is what is being done here. So it is the effluent from the reactor is flashed and the product B is taken out as a vapor stream, and the unreacted A is being sent back to the reactor as recycle. So this is briefly what is happening in this flow sheet. The combined feed of pure A and recycle, pure A and recycle, is partially converted to B in this reactor, which is R100, by the isothermal liquid phase irreversible reaction A to B. And this shows first order kinetics. The reactor effluent is being pumped and flashed across valve V3 to give a vapor product stream and a liquid stream. The vapor product stream is say pure B and the liquid stream is pure A. So the liquid stream is recycled. Liquid stream is pure A. We are assuming that the volatilities of the A and B are widely different, and B is much more volatile, so it can be flashed and pure B can be taken out. So the liquid stream is recycled to the reactor where it is mixed with fresh feed A to give the combined feed. The question we ask is, what happens when the fresh feed flow rate changes? So when the fresh feed flow rate changes, what happens to the process? So what snowball effect we will see? So this you can find out by doing the material balance equations. You write the mass balance equations on the inputs and outputs of this CSTA and the overall process, flash diameter, etc. Also considered the first order reaction rate. But we are saying just presenting the data here. Let's consider F0 is the molar flow rates of the feed and B is the flash liquid streams. Molar flow rate of the flash liquid stream, that means that is the recycle stream. Note how the changes in F0 cause change in B. See, when F0, which represents the molar flow rate of the fresh feed, was 50, the molar flow rate of the flash liquid stream, that means the recycle stream, was 16.7. And when you increase the molar flow rate of the feed, fresh feed, to 150, that means 3 times, the flow rate, the molar flow rate of the recycle stream, that is the flash liquid stream, becomes 450. So several times increase in the recycle stream. So strong can be the snowball effect. Now these days, we have this plant-wide control systems. So every control system will be in sync with the other control systems in the process. Initially, the process could have been separated by using search tank in between two processes, where the disturbances of the process could have been absorbed. But now we are interested in designing and operating a process which is thermally coupled, integrated, and also there is mass integration. Such processes becomes more sustainable and more economic and environment friendly. So always remember the snowball effect of a recycle stream. So the lesson we learned from here that we must place appropriate flow control on the recycle stream. Otherwise, a small disturbance in the fresh feed stream for such a process can cause a great change in the recycle stream. So have a proper flow control installed on the recycle stream. Now, that's perhaps the time we get for discussion on the recycle effect and snowball effect and its snowball effect. Now let's look at one question that came on the forum. How does degree of freedom influences a process plant like petroleum refinery? So degree of freedom is a very important concept. And as engineer, we must know the degree of freedom of the process. Unless we know the degree of freedom properly, we cannot evaluate the process in terms of its controllability, how the process can be controlled. We had a brief discussion on degrees of freedom computation in our previous live session program. It is important to identify what are the variables that are dependent, what are the variables that are independent. And then the relations that exist between variables. These informations will allow us to compute the degrees of freedom. For example, let's say, since you're talking about refinery, we just talked about the case where I said that if the recycle in a distillation column increases, the vapor load can increase, the reboiler and the condenser capacities may not be enough anymore. So for example, let's talk about the recycle stream in the form of reflux. When you consider a reflux, see, you cannot set any value of reflux you want, because that will be linked with the reboiler heat load as well as the condenser capacity. So we have to identify whether these variables are actually independent or they are dependent. Setting any value of reflux ratio is not possible. You may run out of your condenser capacity. You may run out of your reboiler capacity. So such consideration will allow us to implement appropriate control for the distillation columns in refinery. So with this, since there is no other question in the forum, we'll stop our discussion here today. And if you have any further questions, please feel free to post on the portal, and we'll address them. Thank you for joining.
Okay, thank you, sir.
তাহলে এবার লগ আউট করি।
Yes, sir.